Buenas, buenas tardes. Bienvenidos a la conferencia de esta tarde de parte de la IADR División Colombia. Es muy importante para nosotros informarles la calidad de nuestra conferencista invitada, por la cual pues agradecemos su presencia en este auditorio. La doctora Pamela Den Besten es una profesora muy conocida por sus trabajos de investigación y una trayectoria muy grande en los Estados Unidos. Viene de la Universidad de San Francisco, en California. Es autora de múltiples trabajos de investigación y cuando uno, digamos, está dentro de una conferencia de un investigador top, hay que aprovecharla al máximo. En este sentido, queremos que al final tengan preguntas. Los estudiantes pueden preguntar en español y aquí vamos a tener a una persona que nos va a apoyar para que Pamela tenga la respuesta en inglés. Pamela no habla español, indudablemente. Y la conferencia va a ser en inglés. Entonces es importante que nosotros como hispanoparlantes podamos entender un poco lo que es una conferencia o el lenguaje técnico en inglés para que, digamos, nos vamos acostumbrando a ese lenguaje de la ciencia que es universal y que eso fue uno de los motivos por lo cual no va a haber traductores. Nosotros queremos que nuestro país pues ya tenga la misma dinámica de los países desarrollados como Brasil. En todas las conferencias que se hacen en eventos son siempre en inglés y nosotros todavía estamos utilizando traductores. Eso debe haber ya una evolución, un cambio, y esta es la primera vez que vamos a utilizar esta dinámica. Pero indudablemente una cosa es entenderlo y otra cosa es hablarlo, pero la idea es que todas las preguntas en español sean bienvenidas para que la profesora Pamela pueda aclarar todas las dudas. Entonces los dejo en compañía de nuestro conferencista invitado y aprovechemos al máximo y agradecemos nuevamente a ella por aceptar nuestra invitación a Colombia y específicamente a la Universidad del Sinú. Pamela, tu auditorio.
Gracias and hola, and that's all the Spanish I have. So I realize that many of you, English is not a language you understand well. I'll try to speak slowly, and sorry that I can't speak more Spanish, but hopefully you'll understand some of what I have to say. So I bring you greetings from the IADR, and in particular the central office in Washington, D.C., that is responsible for all of the administration behind our divisions and regions and sections. And they are a small group, but excellent. This is the headquarters where all of this. Maybe I'll use this. Yeah. Okay, great. Can everybody hear me? Yeah. Okay. So this is the headquarters where everything happens, where the journals are made, all of the meeting arrangements are made. Louder. Okay, I think they're going to turn it up. Okay. Okay, so for those of you who are IADR members or who are interested in attending an IADR meeting, there we go. Now it's too loud, but That's off. Yeah. I just want to remind everybody that the dates for abstract submission to attend the Washington meeting is October 25th. So if you're doing research and you are interested in going to this meeting, keep this date in mind. It should be a wonderful meeting. It's the centennial. It's celebrating 100 years of the IADR, and so there'll be many events, and it's in Washington, D.C., which is always an interesting city to visit. The other thing I want to bring your attention to is that in the future, in 2023, the IADR meeting will be in Bogota. And so we look forward to, the central office and the board look forward to working with the leadership in Colombia and having students, and a really exciting meeting here. It should be wonderful. So I'm going to talk about tooth enamel. And I know there are a lot of people that are doing all sorts of different types of research. And I want to talk to you about why I've spent my entire career doing studies on tooth enamel, why I found this exciting, and hopefully at the end of the talk you also will. So everybody here, I'm sure, knows that enamel, tooth enamel, is the hardest tissue in the human body, and it is formed by very interesting cells called ameloblasts. And the ameloblasts start out as their epithelial cells, and they start out as a flat epithelium, and then they differentiate to make this really interesting matrix and covering of the tooth that lasts for a lifetime. We all appreciate how important enamel is, because when it's lost, we essentially have major problems with our teeth. And so what causes the loss of enamel? We all know about dental caries, and we all know that, particularly in children, how quickly they can take over and destroy teeth and cause lots of problems for children. Dental fluorosis when it is severe, can cause discoloration and loss of enamel. In amelogenesis imperfecta, when a single protein, in this case a protein called WDR72, is lost, the teeth are essentially discolored, painful, the gingiva is easily inflamed, and this person has a lifetime of trouble with these teeth. And then molar incisor hypoplasia, which is interesting because we see it, but we don't actually know yet what causes it. So anytime enamel is compromised, missing, the teeth are in trouble, the oral cavity is in trouble, the body is in trouble. So just to, and again, probably, particularly the dentists or dental students know this, but just to remind you of this very interesting structure that these cells make, they make hydroxyapatite crystals that are formed in bundles, such as here, that are called enamel rods or prisms. And these bundles weave through each other to form a structure that is resistant to fracture and wear. So it's a very interesting structure that the body forms to protect our teeth for a lifetime. So this is a scanning micrograph of how these prisms interweave through. So how do ameloblasts form these prisms? Well, very interesting. Each ameloblast forms one enamel rod or prism. So this is a scanning electron micrograph of ameloblasts on the enamel surface. And you can see each one of these cells is overlying and secreting proteins to make one rod. And here in a transmission electron micrograph, you can see the outline of where the ameloblasts were and that they are responsible for one enamel rod. So the other interesting thing about ameloblasts is they do all of this sitting on top of the enamel. So I always think of them as cooks making a great stew where they're just dropping things in, and this magic that they're making happens in processes that just occur by mixing things together. So the most important thing about the enamel structure is that these rods are uneven. So this is a three-dimensional reconstruction of enamel rods in a primary tooth. And you can see that they form this uneven structure, which is very important because if they were straight, then this enamel, when you bit down on something hard, would fracture. So it's a very genius structure that these ameloblasts figured out how to make. So when we think about how the enamel is formed, one way to think about it is this is spaghetti that's uncooked. And when the spaghetti is put into a funnel and it's soft, it moves to fill the space. And in the same way, this is again how the rods go through the enamel to make it a resilient and strong structure. So in thinking about, now we understand the structure of enamel, how it is built so that it lasts a lifetime, and how it can do all sorts of things and not biting, chewing, and not break. So what about the ameloblasts? So the ameloblasts are the only epithelial cells that form mineral. There are no other epithelial cells that form mineral. And they do this by continually differentiating. So they start out as flat squamous epithelial cells. Then in pre-ameloblasts, they elongate. Then suddenly they become very columnar and secrete enamel matrix. And then they transition to maturation stage where they remove the matrix, deposit mineral, and we're left with enamel. So as you can understand, when we as dentists or clinicians, when we work on teeth, we don't think of all these processes, but it's actually very, very complex to make tooth enamel. And we have very little understanding of exactly what is making these cells do all these things, where they first secrete, and in the maturation stage, they hydrolyze the matrix, and they transition between the enamel matrix to form transitions between low and high pH. And all of this is modulated by these cells that are sitting on top of this enamel matrix. So Another very interesting thing is that when enamel formation is complete, proteinases go in to remove the matrix. The ameloblasts then endocytose the remaining protein, and what is left are peptides. These peptides are very important because they are the glue that keeps these crystals together. So the peptides left in the enamel keep the crystals intact, keep them from collapsing. And so they maintain the integrity of these glass-like, extremely thin, long enamel crystals. And for years I thought about enamel bleaching. I don't know if that's something that's common here in Colombia, but I think of bleaching as a process that we need to be aware that they may be destroying and removing these peptides. So bleaching makes teeth white. This is we call it a sand dollar. It's a ocean creature. And when you collect them, they're brown. And then when you put them in bleach, they turn beautiful white. And they turn white because all of the proteins are removed and they're left with a porous structure. So I think that we need to be thinking about that bleaching enamel might actually cause some problems. With excessive bleaching, it could be fragile. You could be opening pores that cause sensitivity. So in everything that we do in dentistry, we should be thinking about the structure of the tissues and how the processes that we're using affect those structures. So as I mentioned, when enamel is improperly formed, it can be defective. And one of the, so I've mentioned previously amelogenesis imperfecta. Amelogenesis imperfecta, and I know there are some great work here in Colombia related to amelogenesis imperfecta, but that tells us a lot about the importance of the proteins. But what has been really interesting to me is how the environment, changes in the environment can affect enamel formation. So fluorosis is an environmental effect. So it's where there's increase in fluoride, it causes a defect in the tooth enamel. And molar incisor hypoplasia may also be an environmental effect. So the question is, how do different chemicals in the environment, individual response to the environment affect our enamel formation and how our body functions, and do they work together? So I think enamel has a lot to teach us. So as I said, I've spent most of my career focused on questions related to enamel fluorosis. And this started with a simple observation when I was a dental student. I noticed that this is a cross section, or a section, a polished section of a fluorosed tooth. And you can see, and the brown is a hypomineralization. So I was really surprised as a student to find that in fluorosis, there's a hypomineralization that actually looks very much like dental decay looks, early forming enamel decay. So as a student, I wondered if fluoride can affect ameloblasts to result in fluorosis, can it do similar things to other cells in the body? I was just curious, didn't know the answer, but I thought it was important to find out. So to talk just a little bit more about that, about how before I go on to the next slide. Again, every question that we ask means that we have a lot of work to do. So for me, I didn't know anything about enamel formation. So first of all, to answer this question, I spent a lot of time doing many studies to try to understand how enamel is formed. And then in 2005, I did a study with a neurotoxicologist in rats, and we found that fluoride given to these rats caused them to have different behavior. I noticed that the rats were more easily jumping out of their cages, and so I asked her to test them in her system, and so she found this neurotoxicity effect, and this led me to many more questions, such as to further ask, do the mechanisms by which fluoride affect myeloblasts? Do they have similar effects on developing neurons? And then what about other ion-transporting epithelial cells? One of those cells is the gut epithelium. And so what more do we need to investigate? And these are questions that remain to be answered. And there's probably going to be a lot of research coming up to try to address some of these questions as to what is fluoride doing to cells, and is it similar in various cells in the body? So in that same line of thought, a very interesting property of enamel is that once it's formed, it doesn't change. So it serves as a fossil record, which isn't altered after formation. So if you want to know what happened during formation of the teeth, or what happened during that time of formation, we have a record in the enamel. So we had a really, again, moving on from this question of neurotoxicity, we wondered, as a fossil record, is it possible that enamel could be a biomarker for health risk? So there's many things that affect health, as we've talked about genetics, environment, and just the rate of development. And so thinking about neurotoxicity, could changes that affect tooth formation also affect the developing brain at that same time that the teeth were formed? Can enamel or teeth, for example, primary teeth, which are formed in utero, could they be a biomarker for environmental effects during that same time of formation? And in fact, we found evidence that supports this. In a study in 2010, Professor Boyce examined kindergarten children and measured cortisol in their saliva, and found that children with high cortisol reactivity had thinner and hypomineralized enamel on their primary incisors. And these were kindergarten children, so we were very surprised at this, and particularly when we realized that those teeth are formed in utero. So these are kindergarten children that have high cortisol reactivity, and their teeth were formed in utero. So does this mean their high cortisol reactivity is related to what happened during their fetal development? So cortisol reactivity is a measurement of a child's response to stress. So if a child is given a stress test, or anybody, if they look at the post-test level of cortisol as compared to the basal level of cortisol, and if it doesn't go down, then they have a high cortisol reactivity. So generally, it goes up and then it goes down. So high cortisol reactivity measures a dysregulation of stress response, and cortisol levels are unable to return to baseline. So as I mentioned before, cortisol reactivity in children is associated with previous increased maternal cortisol in utero. So again, if we find high cortisol reactivity in children, and we find changes in the primary teeth, it may be a biomarker of cortisol, increased cortisol in utero, which is a marker of stress. Cortisol is a marker of stress. So since enamel mineralized in utero, this in our study suggested that tooth enamel formed in children with a high cortisol reactivity was under the exposure of high cortisol levels during gestation. So that is a link to as enamel as a biomarker for prenatal stress. And then why could this be? Well, another really recent interesting finding that we realized is that cortisol regulates the expression of clock genes. So we all have these clock genes that are related to the time of day, and they sort of set up a circadian rhythm. They set up a rhythm for our bodies for formation. So it may be that cortisol is acting by regulating clock genes, which could dysregulate enamel formation. So in enamel, we have various incremental lines, and one of these are called cross striations, which which are a marker of daily activity of the ameloblasts. So this again suggests that clock genes regulate amelogenesis. This is likely responsible for daily incremental lines or cross striations. So we have some future research planned where perhaps we can measure the width of these cross striations to understand how it is related to changes in the enamel or toxicity. There are a couple of, for those of you that anybody that knows anything about clock genes, one of them is called NR1D1, and we're looking at that. That regulates DLX and RUNX2, both of which are very important for proteins involved in amelogenesis, for both secretion of matrix proteins and enamel matrix maturation. So this could be one of the mechanisms that we're looking into. And then again, cortisol may be regulating this, and that could be why we see a similar effect relative to prenatal stress and also the formation of primary tooth enamel. It's also, so this actually is, again, this is recent work that a PhD student of mine is doing. And so we looked into this because we were thinking, you know, hormone receptors and ameloblasts. And as we looked at further at a microarray, we realized that ameloblasts express many steroid hormones. So far, we noted glucocorticoid receptor, GABA receptor, and then androgen receptor and progesterone receptor. And we have some other work showing that fluoride changes the regulation of the activation of the androgen receptor, which may be one of the ways that it results in enamel fluorosis. So this is a very interesting area, and the function of these genes in amelogenesis may be clues as to how teeth can be used as biomarkers for environmental effects on brain development. And that just leads me into another thought. For years, everybody's sort of thought about the mouth as completely separate from the rest of the body. And in fact, it is very connected to the rest of the body. The ameloblasts or the odontoblasts have similar receptors, similar function as other cells in the body. The microbiome in the oral cavity influences the gut microbiome. So I think more and more those of us in dental research will have a lot of impact on understanding how oral health regulates and affects development and function in many cells and tissues in the body. So back away from a little bit of basic science to what do dentists think of enamel? Well, much of the work of dentists is us who are dentists, and those of us who go to the dentist, and those of us who take our children to the dentist know that much of what dentists do is to correct the effects of lost enamel. And what we're learning more and more is that dental materials, there are many dental materials, but they all have limitations as enamel substitutes, and some of those limitations are related to neurotoxicity, bisphosphonates, amalgams. And so understanding enamel and tooth formation can possibly help us develop new enamel-like materials and hopefully bioengineered teeth. So what about that? Bioengineering teeth, bioengineering enamel? We've been interested in this for a while, and we many years ago started growing ameloblasts in culture. And we found that in culture, they make the primary enamel proteins, but they grow in these circular cultures, and there's something we call an epithelial pearl. It's you see them in children, and that's essentially what the enamel in culture looks like. It's kind of like this circular mess of matrix, it just in a circular form. So if ameloblasts can't form enamel all by themselves, well, we know that enamel doesn't form without dentin. So what about the dental mesenchyme? So we know that teeth forms by epithelial mesenchymal interactions that move the tooth through this various stages of differentiation. And at this, what we call the Bell stage, is when the ameloblasts begin to differentiate and start to form enamel. So what about the dental mesenchyme? There was a study published in Science in 1980, which I just think was a wonderful study. This was done by Ed Kolar, and they took epithelium from chicken feet, so their plantar epithelium, and they grew it with mesenchyme from mouse molars, Bell stage, and when they recombined this epithelium from the chicken feet and the mouse molars together, they formed a tooth complete with enamel. So this was a wonderful evidence that the signals in the mesenchyme are what drives enamel formation. So can we look at the mesenchyme to understand how to differentiate enamel, and obviously, eventually, how to make teeth? So we did some studies where we actually took a human embryonic cell line and differentiated them to epithelial cells. And we co-cultured those cells with dental mesenchyme from human tooth organs at this early stage of enamel formation. And in kidney capsule and in culture, we were very excited to see this actually looked like an early forming tooth, and this looked like an enamel structure. So it seems that in fact in humans, as well as mice, that this particular stage of the dental mesenchyme could be very important to driving enamel formation. Interestingly then, we took dental pulp cells, which is the dental mesenchyme that's isolated from fully formed adult teeth, and we did the same thing. We cultured them with the same epithelial cells, and we found structures that look like hair, or just kind of look like nothing. So it's clear that this stage of formation in the dental mesenchyme is critical to inducing ameloblast differentiation. So one of the questions that I know some scientists here are working at are, well, that's interesting. What are the key signals that the dental mesenchyme could initiate this cascade of interactions that result in enamel formation? Well, we don't know, but we did do some microarray, and there are certain transcription factors such as MX1, LEF1, LHX8 that are significantly upregulated in the Bell stage mesenchyme as compared to the fully formed mesenchyme. So one of the thoughts that we have as a strategy for tooth regeneration or enamel regeneration is how could we reprogram adult dental pulp stem cells derived from extracted teeth, reprogram them to an earlier stage of dental mesenchyme? Is that possible? And if we could, then we could use those cells combined with any epithelial cells from the buccal mucosa or other source or other places in the human body or differentiated in culture, and could we then grow ameloblasts and enamel matrix? This is a lot of work. We actually aren't actively working on that, so maybe Jaime and his group can work with us and figure this out. But it's very interesting to think of the dental mesenchyme as it's not just one mesenchyme, but it changes throughout differentiation and really can drive the epithelium. So, in summary, what I've presented here is that enamel is a very unique structure. It's formed by ameloblasts, which secrete hydrolyzed proteins and direct crystal growth. These are interesting and complicated cells. When the enamel, that retention of peptides in the fully mineralized enamel are key to its resilience and prevents crystals from breaking. And then this question of, can altered mineralization in enamel be a biomarker for prenatal stress or other environmental effects that we may want to know more about and screen children for their effects? And I used to think that regeneration of tooth structures was kind of a great idea, but a little bit of a crazy idea. But as I think more and more about all the problems that occur with synthetic dental materials, there just really aren't any good ones. I mean, they're good enough, but they all have problems. Then strategies for enamel or tooth regeneration, although it's complicated and it's probably a long time to come, I think is a very important key future direction. So I would like to acknowledge my co-investigators, Yan Zhang, who's a wonderful cell biologist. Ralph Fredlansky did the imaging on enamel. Wu works with matrix, and then Yukiko. Our current PhD students, Ida is doing the prenatal stress. Kay is looking at WDR72, amelogenesis imperfecta, and Michael Lay is looking at how fluoride regulates the androgen receptor. And I want to bring you greetings from my city to yours. This is looking across this is the San Francisco city. This is the Golden Gate Bridge, and it's looking at the city from outside of the city, from across the bay. And it happens to be a day where it's not foggy, so it's a good day to take a picture. So with that, I would answer any questions, and if there's some of this that you kind of understood, but you want to ask questions and understand better, I understand we've got a great group of interpreters here in the second row that can help out. So thank you very much.
¿El otro micrófono dónde está? ¿Hay alguna pregunta que quieran hacerle a Pam? En español, no hay problema. Tenemos la ayuda de Andrea de la Universidad del Bosque para la traducción. ¿Alguna pregunta, inquietud? Ok. ¿Spanish?
Bueno, me encantó lo que nos compartió la doctora Pamela. Esta mañana estuvimos en una presentación de los estudiantes de Univalle que mostraron un proyecto de la infección del virus Zika, que es un virus neurotrópico. No sé si la doctora haya hecho estudios que muestren si la infección viral puede afectar también células como los ameloblastos. ¿Te toca con el mismo?
Because it could again. Sorry. No, we haven't, but I think it's a very interesting question. Again, because if it affects some cells in the body, it could affect tooth-forming cells and give clues to when things occurred. So, no, we haven't, but it's interesting.
I can help about that because you know I am virologist.
You know who I am?
Yo he trabajado un poco con Zika, tenemos algunos estudios, pero en diagnóstico y patogénesis de Zika en enfermedad infecciosa, pero no en esta parte de desarrollo. Tenemos un proyecto en desarrollo de Zika con sistema nervioso, que es lo que primero se encuentra. Realmente lo que está sucediendo en esos casos es un retraso general de la maduración de los dientes, adicional al desarrollo y a la infección, al efecto inflamatorio de la infección en el sistema nervioso central y en el desarrollo craneofacial. Entonces, eso, desafortunadamente es un efecto mucho más global que directamente en el ameloblasto. Entonces, la advertencia que hay que hacer es que, primero, como virólogo, les cuento, Zika no ha desaparecido, sigue circulando, sigue infectando personas en el país, sigue infectando mujeres embarazadas y sigue causando defectos en el desarrollo global del sistema nervioso, pero también de estructuras craneofaciales muy, muy severas. Ok, ¿otra pregunta?
Gracias, Jaime. ¿Cómo puede la doctora obtener el cultivo de ameloblastos en el laboratorio? ¿Con qué señales, con qué factores de crecimiento y si lo logra por diferenciación de células madre?
Actually, we've isolated them from developing human teeth that were obtained from abortions, but our primary cell line is from pig. The cells are actually quite easy to culture. I've realized this recently. We've done this for years. And if you take the enamel layer off and transfect them with SV40 or any, they grow quite well. And the trick is that they start to lose expression of proteins at about passage 12 to 15. So it's a matter of expanding out early passages. And for years, we've had these cells, and I just didn't feel good about them or what they were doing, but they do express all the matrix proteins, and I think I'm actually thinking about now finally writing a paper because it's not difficult, and it's something that a lot of people would probably like to know how to do. So I can give you a protocol.
¿Alguna otra pregunta?
Buenas. A mí me gustaría saber si, digamos, tratamientos ya de ingeniería tisular en odontología vienen siendo, digamos, ya aplicados o con las investigaciones que plantea la doctora, ya se están realizando algún tipo de terapias o algún tipo, pues, de cambio de la forma en que ejercemos la odontología.
You want to ask if they want a translation?
¿Quieres que traduzca la pregunta a español? O sea, la respuesta. Está preocupada si quiere que traduzcamos las respuestas también de lo que está diciendo. Okay, we'll do it.
I should have done that earlier. Yes, and I think we're all trying new ways of prevention. There's a lot of use of silver diamine fluoride in the U.S. for children that seems to be really effective. My interest is also looking at what other factors can help prevent dental decay, like environmental stress. Are there things besides just brushing the teeth that can help make the tooth enamel stronger? So, I don't know if that makes sense.
Sí, están tratando de claramente tener una odontología más preventiva y
Go ahead. I couldn't understand what you said.
yeah,
What?
more preventive dentistry, what that you're trying to conduct.
So we're doing studies using silver diamine fluoride.
Sí, están haciendo estudios donde están utilizando fluorodiamina, básicamente pensando en esta parte, en hacer algo más preventivo.
But how about the structure, the enamel regeneration in situ, enamel regeneration? I think it's.
Yeah. No, we haven't done any of those studies. I think it's very important, and it's something that we need to work more in the future. But no, we haven't done anything in humans.
No han hecho todavía ningún estudio en cuanto a modificar la estructura del esmalte. ¿Alguna?
¿Más preguntas? Yo quisiera preguntarle a Pam sobre los estudios con células madre embrionarias, las dificultades éticas de conseguir y adaptar y trabajar con células embrionarias, STEM embrionarias, que siempre es una restricción muy grande en otros países. Las dificultades técnicas y éticas.
For the
Yes, the embryonic human stem cells.
Well, that is a very interesting question, because there's a clinic in San Francisco that performs abortions, and at that point
Ellos fueron a una clínica en San Francisco donde se hacen abortos.
and so at that point the tissue is considered cadaver.
So, en ese punto el tejido se considera un cadáver.
So then we can collect it and
How many fetuses? How many fetuses?
one.
One?
Yeah.
This one?
Yeah.
Entonces, en ese momento ya se puede recolectar la muestra.
Yeah, but I mean, you mean to grow cells?
Okay.
Yeah.
Yes, yes.
Yeah.
¿Alguna otra pregunta, alguna inquietud? Como ustedes ven, la doctora Pamela es la directora del Centro de Atención para Niños en San Francisco. Creo que puede ser útil para algunos de ustedes, que si quieren contactarla a través de la página de IADR. Ella es la futura presidenta de IADR del año entrante.
Bueno, primero que todo, muchas gracias por la presentación. Y pues mi pregunta es, ¿ya existen estudios sobre regeneración celular en otras partes del cuerpo, como la piel, como regeneración ósea? Y todos ellos parten desde el principio de que se hace por fuera de un organismo in vitro y luego ese material se introduce en el cuerpo como reemplazo del órgano que se desea reemplazar. ¿En la odontología también se pretende a futuro hacer esto mismo o se pretende directamente que sea regeneración a partir del mismo cuerpo?
I think those are questions that we're just going to have to do the research. I think at this point, I don't know. I think maybe my own thought is if you could, as a dentist, take an impression and then make a material to fit that cavity, and then make a dental material and then glue it in, could be a first step. I think he understood.
Ella dice que pues claramente no sabe que a medida que se vayan haciendo las investigaciones se va a ir resolviendo este tema. Sería perfecto si pudieran hacer un tejido afuera y después ponerlo como si fuera un pegante, un colbón y volverlo a poner dentro del mismo cuerpo.
Basically, it's a complicated area, and as I said, it's something that a few years ago I thought, it's too complicated. We have good enough materials. Why bother? But I do now think it's important, and it's just going to take a lot of research and a lot of people just trying different things to move it forward.
So, es un área muy interesante, pero con el tiempo va a venir trayendo todo ese tipo de la respuesta. ¿Alguien tiene otra pregunta?
Thanks, Doctor, for your conference. I have a question. Do you have any idea about the role of the receptors that your student found on ameloblast?
Which one? ¿Cuál es el?
Que si tiene alguna idea de los receptores de los ameloblastos que encontraron sus estudiantes. Las hormonas.
Sorry?
Hormones.
Oh yeah, yeah. It's very interesting. So I think the only way to know is to look at mouse models. So we know that the androgen receptor is important in mineralization, and so it's actually when it's activated, it activates the proteinase KLK4. KLK4 is a primary enzyme in enamel formation, and it's also very important in the prostate, which is how we know that androgen receptors modulate that. So we know that, and then the others we don't know whether they really function or whether they can just be modulated, like cortisol.
Pano dice que la posibilidad de que sobre todo los andrógenos, las receptores de andrógenos estén involucrados en la expresión de la calicreína 4, que es una de las enzimas relacionadas con la eliminación de las proteínas en el esmalte y afectando la maduración. Entonces podría haber un defecto asociado al género o al sexo del animal.
We have some mouse models, and we're looking at the teeth, and that's always a big question to figure out exactly what's going. But they're doing something, so it's interesting.
Ok, muchas gracias. ¿Alguna otra pregunta, inquietud? Quisiera recordarles que la doctora Pamela Investen es la presidenta electa de IADR. IADR es la International Association for Dental Research, y el año entrante será que hace una reunión de investigadores mundial a la que asisten normalmente entre 5.000 y 6.000 investigadores de todo el mundo. Normalmente de Colombia participamos entre 35 40 profesores y estudiantes en ese congreso. En este momento están abiertas las inscripciones para abstracts, para resúmenes. Si ustedes quieren someter sus resúmenes, no tienen que ser miembros todavía de IADR, pueden presentar sus resúmenes en inglés, obviamente, ser evaluados, y si son aceptados, pues se pueden inscribir a IADR, participar en el congreso. El año entrante será el congreso del centenario, el congreso número 100 de la IADR en Washington, en Estados Unidos, y presumimos que va a ser el congreso más poderoso de los últimos años en investigación en odontología. Es una gran oportunidad para conocer a los profesores como Pamela, como otros profesores, otros 2.000 o 3.000 profesores de todo el mundo que hacen investigación, que son los profesores que ustedes estudian en sus libros, que ustedes leen en sus artículos, estarán allí en ese congreso. Entonces es muy importante participar como estudiantes. Si ustedes entran a la página iadr.org, van a encontrar que hay becas para estudiantes, y hay sistemas y hay posibilidad de pedir recursos para participar en ese congreso. Entonces, si quieren, efectivamente pueden contactarse a través de la página o en Colombia con Farid González, el presidente de la IADR División Colombia, para participar en ese evento. Entonces queremos invitarlos a ser parte de la IADR, a conocer las actividades de la IADR y darle un agradecimiento gigantesco a Pam. Thank you very much, Pam, for your help here. Thank you.
Bueno, agradecemos por su presencia. Los invitamos en el auditorio Sinú. Se está llevando a cabo una actividad de la IADR de concursos de premios. En estos momentos todavía faltan como 6 o 7 trabajos. Entonces ya la actividad en el auditorio se termina ahora, y ojalá todos puedan desplazarse al auditorio Sinú a acompañarnos. Está lloviendo, así que saquen paraguas. Muchas gracias y feliz tarde. Pamela, thank you. Thank you. Very interesting. Guillo,
Okay, that's what I tried to do. Yeah. Oh, wonderful. Oh, fabulous.